All right, this is going to be the first lesson in just the astronomy class, which is a review of everything you've learned, back in elementary school, where it's going to be just some basic relationships between the planet Earth and its orientation relative to the sunshine, and some basic information about time zones and seasons and meridians and degrees of rotation and the tilt of the axis, all that sort of stuff, what causes day and night. I mean, stuff that you've known for a long time, but we got to start somewhere, so here we are. But anywho, this is the planet Earth, okay? And I've shown you where it is relative to the sun. The first thing I'd like you to notice is it makes a straight line to the sun, a flat plane, all right? It's not tilted up above it. It's not below the sun. It's in a nice level plane with the sun. That's what I want you to remember, the level plane that the Earth and the sun make relative to each other is the plane that is the solar system. All of the planets lie along that plane. So Venus could be here-ish, Mercury could be there-ish, and I would have to stay on that same level to get out to Mars and Jupiter and Saturn and all that. I'm not going to go way up there to get to Jupiter and way down there to get Mars. We're going to stay on that flat plane, okay? That term is called the ecliptic. All of the planets and the sun and all of the moons, everything lies on that ecliptic plane, okay? Now, when you get to a much more advanced class, Einstein will tell you that there is some curvature to the universe, but for now, all of us that aren't Albert Einstein, the simplified version is good enough. It's just a flat plane called the ecliptic, all right? What you guys also know is this then is the North Pole. That's the South Pole of the planet Earth. You can tell it's not vertical, it's not perpendicular relative to the plane of the ecliptic. It's tilted. That tilt happens to be 22.5 degrees, okay? So 22.5 degrees is how tilted it is from vertical. It's also how tilted the equator is from the ecliptic from horizontal. So there's a 22.5 degree incline right there relative to the flat plane that is the ecliptic, all right? Tilted at 22.5 degrees. What you'll learn in one of the next videos is 22.5 degrees north. Latitude is the Tropic of Cancer, 22.5 degrees south latitude is Tropic of Capricorn. We'll learn why they're called Cancer and Capricorn in a bit, but the number 22.5 is very, very significant because that happens to be the tilt of the Earth from there, all right? What I also want you to realize is you can tell this then is North and South America. You can tell this is the east coast of those continents. This is the west coast of those continents. So when the planet Earth rotates, it goes this direction, all right? Hopefully you can be able to tell we always rotate towards the east, So you guys know folks in New York City see the sun rise before folks in California. Folks in New York City see the sun set before the folks in California do. They see the last sunset out overlooking the Pacific Ocean out there. And then this then is obviously Asia and Australia, India, Africa, and Europe, and all that sort of stuff. Then there's the Atlantic Ocean. But we always rotate towards the east, okay, that way. Okay. The other thing I'd like to show you using this camera and our perspectives is from directly above the North Pole. All right, let's pretend in our headsies we're spying on Santa. The direction the Earth rotates as viewed from directly above the North Pole is counterclockwise, CCW. All right, please remember that, CCW. Okay, counterclockwise is viewed from above the North Pole. So again, we're going this direction here. The other thing that is going to be related to is the direction that all of the planets orbit the sun. If we could do the similar view that we just did for planet Earth now, if we could hang out directly above the sun and look down from above its North Pole, all of the planets would also orbit counterclockwise around the sun, okay? So what that means is if I were to ask you which direction not only is the Earth rotating on its axis, but what direction should the Earth move if it's revolving around the sun? Would I go, or would I go, hopefully you can see that if you're from above, we're going to go counterclockwise. So the direction of the Earth revolves around the sun would be this way, the way I have it oriented in the classroom, as viewed from above the sun, counterclockwise, the same way as when viewed from above the North Pole. The Earth rotates counterclockwise. All right. Another thing to just remember. Again, I'm putting the camera here. You can kind of see where the sun is. Right, it's over there. If we're on the side of the Earth that's obviously facing the sun, we're obviously talking daytime. We're talking nighttime over here. That's easy. If you're in a direct line with the sun, then that's what we call noon. And knowing the direction the Earth rotates now, I have to go this way to get to where folks are seeing the sun set. So this is going to be 6-ish p.m. here. We keep going. The exact opposite side is midnight. Keep coming here. Now we're dancing around 6 a.m. as the sun is rising. And again, we're back to 12 noon here at that location that's in a direct line with the sun. Keep going. So anyway, different folks or people at different locations on the same planet are experiencing different times, which gives you time zones, okay? First thing I want you to or think about is if you're standing on the surface of the Earth, you're obviously perpendicular to the surface, right? And it doesn't matter if you're here, which I have pictured in Canada, or down here, which is in Chile or Peru. You see, it's still perpendicular to the surface, even though here I'm pointing downwards, relative low. Here I'm pointing upwards. But please don't associate our location in the classroom with up or down, okay? That's got nothing to do with it relative to the planet Earth. Perpendicular to the surface is going to be straight up, what I call Paula Abdul, straight up. Down here, straight up, even though it's oriented in a different direction, is radially outwards, straight out of. So that location in the sky, which for this particular observer going straight up would be kind of on the ceiling-ish, their location in the sky that is directly above you is called your zenith. All right, the location in the sky directly above you. So if I go straight up, I'm hitting a zenith. The folks down here have a different zenith, even though they're still straight up, but it's pointing somewhere in the southern hemisphere. So there are stars in the southern sky that they could have at their zenith. All right. And if I take an imaginary line and go from the North Pole, connect it to the South Pole, and I have it go right on my zenith in the sky, then I have my own personal meridian line. And that's what the M in AM and PM stand for, is your meridian line. So connect north to south, go through whatever spot you're standing on the planet Earth. That's your personal meridian. But if you then extend that meridian out into the sky, there's your meridian line at your zenith. And so as you're approaching that meridian, what I want you to know, that's going to be AM. That's anti-meridian. So the AM hours are folks who are approaching the meridian. And when the sun is directly above you at your meridian, or not directly above you, but at your meridian, that's when we call it local noon. So whatever meridian line you're on determines local noon. That determines what time zone you're in. And you guys all know time zones, right? The first time zone, they started out in Greenwich, England. They called it GMT. There's something called a prime meridian. They replaced GMT now with what's called UT, Universal Time. The reason they call it universal is because it doesn't matter where you're at in the universe. Folks on the space shuttle, right, or in the space station. What time is it in the space station? They follow universal time, which means it's whatever time it is right there in the United Kingdom at what we used to, or we still do, call the prime meridian, time zero. All right? Everything on the planet Earth starts relative to that. You got to start somewhere. They just started there. Now, what you know, or I showed you before, if you're hanging out here, it's going to take 24 hours for you to go all the way around, right? So if you go all the way around, boom, in a 24-hour time period, you've made a 360-degree rotation in 24 hours. So if we take 360 degrees and divide it by 24 hours, we're going to get 1.5. or I'm sorry, if you take 36 and divide it by 24, you get 1.5. So if you take 360, you'll get 15. So 15 degrees per hour. That's what I want you to remember. There are 15 degrees of geography on the planet Earth between time zones, and they're labeled on this particular globe. Can you tell when it focuses here? That's going to be 0. That's meridian 0. That's the prime meridian. You can kind of ish read that. I'm sorry, it's a little fuzzy. It'll take some time to find itself, but there's 15. So that's one time zone right there. 15 degrees. There's 30 degrees, and that's going to then be 2 time zones. There's 45 degrees. That's then 3 time zones. There's 60 degrees. That's 4 time zones. And I'm going to go north here, and we're approaching the United States here. We're just now hitting Newfoundland and Nova Scotia, that kind of thing. Well, not quite to Nova Scotia, but we're just hitting Newfoundland. Okay? And then if we go one more time zone over is when we hit the east coast of the United States. That's what we call Eastern time. All right? New York, Boston, Philadelphia, and where we're at, it extends all the way into the edge of Ohio and into Indiana there. Where I'm at is Cincinnati. So we're in the Eastern time zone. So that's universal time minus a certain amount of numbers, a certain amount of time zones. So there again is the meridian. So there's 1 time zone, 2 time zones. There's 45, the 3rd time zone. 4th time zone, the 4th time zone is where Newfoundland is. The 5th time zone right here is Eastern Standard. So Eastern Standard Time is what's called UT, or used to be called GMT, -5. We're at Universal Time, -5 now is what they call it. And one more time zone over is 6. And look where that's labeled as its meridian. That's a 90-degree meridian right there. Okay, that's 1/4 of the way around the planet. So folks in Cincinnati, you're pretty close to that 90-degree meridian. We're in the 80s-ish. So we're 1/4 of the way around. And then I want you to notice there's the 2nd time zone. That encompasses the central part of the United States. Another time zone encompasses most of the Rocky Mountains. That's what's called Mountain Time. The 3rd time zone from Eastern is where California is, and so that's Pacific Time. That's where the folks in California, we're 3 hours behind us. Then you have another time zone that's 4 hours behind Central, or behind New York Eastern Standard. And 5 time zones is where you bump into Hawaii. So our friends in Hawaii are 5 hours behind our friends in New York City. So these folks are trying to catch up with the rest. But then you can see where it says 180 right there. Now we're halfway around the planet Earth. That's 180. That longitude 180, then it starts to count down. That's all known as the international date line. We've gone to 180. Now we're getting closer. 165, 150, 135. So this is when it changes days. So this is where if it's when you go from the international date line, subtract a day going east, add a day going west. So these folks are trying to catch up. So now if it's Sunday here, it's going to be Monday there. If it's Monday there, it's going to be Sunday there. So that's where you change what day it is. And then you start counting down again. There's 105, there's 90, 75, 60, 45. And here again is that 0 mark back to the prime meridian. So that international date line is what changes things. And it's smack in the middle of the Pacific Ocean, which makes it pretty convenient. Please remember 15 degrees per time zone, and we always rotate that way. Now, to avoid confusion, what they usually say is these latitudes, see how they're both labeled 15, or longitudes both labeled 15, both labeled 30. They'll call this plus 30. They'll call this minus 30 because you're either ahead or behind of universal time. But remember that. But you guys all knew that universal time goes right through there. So there's a little bit of the relationships between time zones, how many degrees there are in a time zone. The reason why we have time zones is because solar noon, again, when the sun is right at your meridian, that kind of defines solar noon. And then the exact opposite of that is midnight. And the diurnal cycle is what causes day and night. But anyway, that's the first one. It's hopefully pretty simple. I'm going to get a little more in depth with that in our next video. Thanks.